Um, right, let me also just take a few minutes just to make sure that I have my Slido and Zoom set up in a way that I can hopefully see everyone's questions. So let me move this back out so I can try and actually see the chat. Oh well, for unfortunate reasons that I don't understand, when I try and access the Zoom chat, I just get a transparent window. So I'm not going to be able to see chat, but hopefully anyone who is hopefully other
We'll help you.
uh,
Yeah.
yeah, exactly, excellent. But I do have Slido up and on my secondary screen, so I will try and keep an eye on that, and I'll try and answer things as we go along. Okay, so yeah, so I think some people might be having access issues like me for the Coffee Casa instance at Nebraska at the moment. So I've jumped onto the University of Chicago's cluster, their Coffee Casa instance, and I'm going to try and just set up some things here as we go. But so if you're interested in following along, you can do so there. Also, if you just clone the GitHub repository locally, then basically this statistical inference directory under the Analysis Grand Challenge 2022 workshop should basically have most of the things that you need in it. And we'll try and take that as we go. Okay, and then today I'm also, yeah, as Alex mentioned in that nice introduction, we're going to be trying to cover a few things. We're going to be trying to cover statistical inference using pyhf as well as cabinetry. Because I'm usually pretty bad about doing time estimates on this, I'm intentionally tried to cut things a bit short. So I'm not going to be diving too much into the actual model specific building for either of these libraries. If there's time at the end, I'm happy to try and do that. But I figured in trying to keep the focus at this workshop should be hopefully on trying to do things with it. And so I'm going to more focus on pyhf and cabinetry's Python API and try and show some perhaps more real world examples of how you might do things with them. But I'm obviously happy to try and answer questions as we go along. Okay, so to begin with, we already had everything kind of set up on the Nebraska coffee cluster or Coffee Casa. And so I'm just going to really quickly set up a necessary environment. Okay, so, oh, also, sorry, if you're following along and if you're under the Analysis Grand Challenge directory or GitHub repository, please go ahead and just do a git pull, because I was earlier today making some small tweaks and modifications when I found typos and bugs in my own contribution. So you make sure you get the latest there. Once we do that, we're just going to dive into the workshops directory and then the Analysis Grand Challenge Tools 2022 directory. And then one more time into the Statistical Inference directory. So when you're there, you should then be in this is the equivalent directory to this path in GitHub. Here, let me also bump this up on, so I have both of my windows hopefully enlarged. Also, people should yell at me if this text isn't big enough to see on screen. Okay, so we're going to first just set up our environment. So if we cat here, we see that we have a requirements.txt. This is going to have all of the dependencies that we're going to be using throughout this particular workshop. The Coffee Casa clusters have most of these already installed, but we're also going to be using a library called Feickert, as well as some additional visualization libraries. So we're just going to, given that we're also inside of a a K8 pod that's running on these clusters. I'm not going to bother with actually setting up a virtual environment so that we can make sure that everything works well with notebooks as well. So I'm just going to go ahead and directly install into the default virtual environment that are set up with the pods. So we're just going to do python-m pip install -r requirements.txt. And so we're getting funcx and jax and a few other things. So these are just going to be some necessary libraries for us to use today. And if you're following along at home locally, then you're going to want to do that anyway, but hopefully maybe do that inside of a virtual environment. Okay, so, oops. Okay, so now we should have everything installed locally. So we can go ahead and get going. And the first thing we're going to do is we're going to jump into this pyhf intro to HISFactory notebook, where we're going to just quickly cover the HISFactory model as specification, as well as also the Python API that we have for pyhf. Before I go any further, can I have somebody give feedback either verbally or on Slido on how things look on screen? So for example, so what do we do as experimentalists? Is this visible well enough, or should I try and bump the text one more?
Maybe go one more to be sure that it's fine for everyone. I think that's great.
Okay, excellent. Sure. Thanks for the feedback, Alex. Right, so yeah, so pyhf we're really striving for this to be a library to perform statistical inference based around, and we've chosen to have this be based around the HISFactory family of bin statistical models. So we're just going to try and dive in real quickly and understand how you can use pyhf's Python API to be able to try and build and then perform statistical inference with HISFactory. So to begin with, we're first just going to do some imports that we're going to use throughout this example. And then the very first thing we're going to do is we're going to just we're going to build a very, very simple model. And as pyhf has this simple models module inside of it, which allows us to basically provide kind of teaching examples on if you just want to create kind of a very, very simple model, like to try and like test out an idea, this gives you a very quick API to be able to do so without having to write out the JSON yourself or use something like cabinetry to try and actually compile your specification. So we see that we have a model object. But if we actually want to see what's inside of this model, then we can just use JSON to dump out the specification. And if we do this, then we see that we have basically a JSON specification for the entire model. And this is the pyhf specification for HISFactory that we use. So just to kind of get some jargon out of the way real quickly, we have channels, samples, and modifiers, as well as channel samples and modifiers here. And channels you can basically just think of as the different analysis regions that you're going to be looking at in an analysis. Samples are just the components of your model that are so basically the different physics processes that are going to be contributing. And then modifiers, these are the this is basically the name for the for different systematic uncertainties and additional constraint parameters that exist inside of the pyhf specification, and which you'll use to actually try and control your fit to some extent. So this very simple model here, we see it has one channel, so we basically just have one analysis region. And in it has two samples. It has a signal sample that has just two bins in it. So we see that this data field has just two components to it. And then associated with the signal is this normalization factor modifier that we call mu, and that hopefully is suggestive enough to indicate that this is going to be our signal strength parameter that we're going to be basically fitting at the end of the day. And then we also have a background component in this model as well that, again, is just 2 bins. And associated with this background component, we have an uncorrelated background uncertainty where there's, and where these basically represent, the data here represents an absolute uncertainty, so basically a count that corresponds to an uncorrelated shape systematic on both of the bins. And so in doing so, these uncorrelated shape systematics, they end up adding 1 parameter per bin to the entire model. So basically the model receives 2 additional parameters, that 1 shape systematic parameter for 1 for each bin. Okay, so and so basically, if we actually look at these numbers, then we can see that since this this uncertainty is an absolute count for something like a shape systematic, that this essentially corresponds to, for the first bin, a 10% uncertainty, and for the second bin, this corresponds to a 20% uncertainty. And so this is just kind of, given the way that we kind of quantified this up here at the top, where we said that we had our background component, and then the background uncertainty was 5 and on 50 and 12 on 60. That's how this shakes out. Okay, so this is, we don't really need to get too much into the specifics here right now, but this is basically just showing you that we have a JSON specification which fully defines everything inside of here, that fully defines the model. And then if we actually interrogate the model a little bit more with this model configuration API, we again see the same information, that we have a single channel model, and in this single channel model, there are 2 bins, and these 2 bins are parts of a background and signal component of our model, these samples, and the modifiers that we have associated with these samples are a normalization factor, as well as then an uncorrelated shape systematic, which tacks on 2 additional parameters to the model. Okay, so we also see, though, that there's this auxiliary data component, and that might be a bit confusing, because that I would assume that's probably confusing if you're not familiar with HISFactory in general. Given that I'm already 10 minutes in, though, and so I'm beginning to kind of wander in how I'm talking, I'm going to just quickly summarize this by just saying that this auxiliary data is controlled, it basically is the air quotes like observations that are determined from the actual model prediction components themselves, and those go into the auxiliary constraint parameters, and these are used basically just as kind of nominal values to control the fit during the entire process. So we represent them as auxiliary data because they come into the observation component of the auxiliary chunk of the full model specification. We have this main component of the HISFactory model, which is this product of Poissons. And then we have this auxiliary component of the model, which is the essentially these constraint models. And so these auxiliary data are essentially the parameters that end up showing up in the observation components of these auxiliary PDFs. Out of interest of time, I'm not going to go into that more now, but that's just kind of some terminology. Okay, so if we actually look at trying to do some quick model prediction now that we've introduced the concept of the model. If we just ask the model for a prediction without giving it any parameters, then it will complain to us and say, hey, you need to give me some model parameters to begin with. And so if we now give it just kind of default values of 1 for everything, then we actually go ahead and get model predictions out. And the reason why we are getting, so the reason why we're putting in 3 parameters, so we're putting in 1 for 3 different parameters here, is because the parameters that we have in our model are 1 parameter for the normalization factor for the signal strength, and then 1 parameter per bin for this uncorrelated shape systematic. So we're just putting in default values of 1 for all of these, and then the model is then taking these parameters and making model predictions. And the model predictions it returns are both the first 2 components are for the actual main components of the model, and then the second 2 are for the auxiliary components. So if we see, to try and highlight this more clearly, if we now ask for the model predictions with this auxiliary data turned off, then we see that we're just getting model predictions for what the actual bin counts would be. And we provide APIs for being able to get just the expected actual observations as well as the expected auxiliary observations. Okay, again, in the interest of time, I'm going to skip over the ordering of the model parameters. I'll note also that all of this particular tutorial that I'm kind of working through right now is just the first introductory notebook out of the pyhf user guide and tutorial. So all of this is publicly available as a Jupyter book that you can run through as well. And then similarly, in the interest of time, I'm going to just skip over this parameter multiplicity, where basically this is just showing in more depth with the API that, as was mentioned, this uncorrelated background uncertainty, which is a uncorrelated shape systematic, it basically is contributing 2 parameters, even though we represent it in the model as just this constrained by Poisson parameter. It actually, if you ask how many parameters are really in this family of parameters, it tells us 2. Okay, and then again, because I want to make sure that I give at least 10 minutes to both the other 2 components of the tutorial, this is also just showing that we have an API that allows you to do suggested initializations and suggested bounds. This is helpful if you're just trying to get a fit up and going. And then it can also tell you if any of the model parameters are pinned to specific values. So given this, we can now use this API to ask for some suggestions from the model configuration for suggested initialization values, and then we could ask for model predictions for the actual observations. And so we would get, given the current model parameters, we would get expected model predictions for 55 counts in the first bin and 70 in the second. But now if we wanted to say, okay, that's predictions with both our signal and background components, what if we just wanted to try and get a background only model prediction? Then, well, we can ask for the parameter of interest, which is our signal strength, where that model actually lives. And we can then copy our initialization parameters and then tell it that the component that corresponds to the signal strength, that we want to set that to 0, and then as for background predictions, and when we basically kill off the signal, so we have background only, then we would get model predictions of 50 and 60 for the first and second bins as compared to 55 and 70. Okay, so now we can move on to model inference, where if we go ahead and actually construct the observations that we're going to be using, which would be, we're now saying that we performed an experiment and we actually made observations of 53 counts in the first bin and 65 counts in the second bin. The total observations we would then say are those observed data plus the auxiliary data from the constraint PDFs. And then when we go ahead and evaluate the model, log PDF, using the parameters that correspond to the background only model as well as the observations, then we arrive at one value, and if we now use the full model, then we arrive at another. So this is just demonstrating that we have, the ability to kind of interrogate specific components of the actual PDF, and then perform, if we want to perform maximal likelihood inference, we can do that as well. And then the thing that we really care about the most is actually doing hypothesis testing. And for that, we provide this, in the interest of time, I'm going to skip these details, but the probably main API that people will be using is the inference modules hypothesis test, where if we're saying that we want to test a signal strength hypothesis for our model of 1, and then we have a set of observations as well as our model, and we have a particular test statistic type that we want to test, and we want to get not only our observed CLS values, but also our expected CLS values, where the CLS values are a modified p-value. We can evaluate this, but for the model that we chose, the test statistic Q is a test statistic that ends up being sensitive to a test statistic that can allow forgoing both positive and negative, but if we're trying to perform a given the bounds that we have for this particular model that would correspond to some sort of search, we would want to be using a test statistic that would assume that the signal component is strictly positive in its contributions. And so we would want to be using what's called the alternative test statistic instead. So if we go ahead and, as we see here, we have our model be bounded at 0. So if we go ahead and rerun this with the alternative test statistic, then we actually get observed and expected CLS values without any complaints. And then now that we have this, we can also perform upper limit scans, and we provide an API to do that quite nicely. So we can say we have a value of test, we have a range of test hypotheses that we want to check our parameter of interest at. So we can set up just basically a scan and perform inference over all those values to arrive at an upper, in this particular example, given that we're using alpha 0.05, a 95% confidence level upper limit. And if we want to now also visualize this, then we can go ahead and use our Brazil band API to try and actually make a visualization of what these hypothesis tests looks like. Okay, so I've already used up half the time, and so I'm going to quickly transition away from just going over the API to then try and show this in use. So this is more just trying to demonstrate that we have an API that allows you to try and quickly construct models and then actually perform inference. If we now go ahead, I'm going to switch back to the README for a second, just to try and cover a few things. If we actually want to try and perform real world inference with, for example, trying to perform statistical inference for probability models that were published for a particular experiment to HEP data, we can do this, and we can kind of do this quickly at scale with a library called FuncX. So FuncX, linked here in the README, is a function is a distributed function as a service platform. And this, the long and the short of this is that this allows you to essentially set up highly efficient and scalable function as a service on HPC systems, for example. So at the University of Chicago's River Cluster, Ben Galuski has deployed for us a FuncX endpoint that is running and connected to the Kubernetes cluster there, so that there's many nodes that are available for us to actually try and spin up and distribute a thinning workload across. So the next thing that we're going to do is we're actually going to I'm going to access this FuncX endpoint at the University of Chicago, and we're going to download all of the probability models from the published Atlas Run 2 SUSY search for electrolinos that was published on HEP data. We're going to take all those probability models, we're going to download them, use FuncX to serialize them, and then distribute all of those out to different endpoints to try and run very quickly and efficiently and try and actually get the CLS values back from them. And so this is essentially, we're going to attempt to spin up and run across the entire analysis in just a matter of minutes or so. So, okay, so this is going to require, again, just a few short minutes of setup. So in the repository, there is this there's this fit funcx function here, or fit funcx Python program here that we're going to be running in a second. FuncX also requires the use of Globus to efficiently distribute these data. And so we're going to first authenticate with Globus to try and set everything up. So the way that this is going to happen is I'm first going to, since I haven't run, well, actually, let me make sure that I don't have anything here. Yeah, there's nothing there. So I'm first going to initialize this by just actually trying to run the script, which is going to call out to FuncX it's going to call out to HEP data to get everything, and then it's going to serialize and distribute functions to FuncX. Before I do that, though, it's first going to ask me to authenticate with Globus. So Globus is a service that I believe most people should actually already have access to. I'm already logged in, so I've authenticated, and now I get this authentication key that I'm going to post in here. Oh, this is actually also going to fail because I don't have my endpoint. So to be able to access the endpoint, you need to authenticate to show that you should be able to get there. So I'm going to upload my endpoint ID that I have access to locally. So here on my local machine, I have this endpoint ID text file. And now if we run this again, and I'll run with time, then now we should be able to properly authenticate, and since we're not getting an error message, things are starting to spin up. We will get an error message right here, but this is actually benign. This is just a small kind of benign bug that's on the deployed FuncX service at the moment, but pretty soon we'll start to actually everything is running expectedly, and pretty soon we'll start to actually see that we're getting results coming back. This should hopefully take under 2 minutes or so. Yeah, so as we can see, we're starting to get back different mass hypotheses that were being tested, and we're getting back their observed and their expected CLS values. And the script that I'm running is intentionally putting those out to screen as we receive those all back. Okay, great. So that's finished running. And so we fit all 125 mass hypotheses in 54 seconds. So that included the time to download everything, serialize the functions, distribute to the FuncX endpoint, have the jobs be spun up and run, actually perform the inference, and then send everything back. So that means that we're able to do things in a pretty short, be able to turn statistical inference jobs that might have traditionally taken minutes to hours into kind of a near interactive experience. We've also written out all of these individual results into this results.json file. For those of you who are following along, I already preloaded a results.json file into this repository as well, so that you didn't have to run this. And if you want to continue to follow along while we now actually plot up these exclusion contours, you can do that as well. So we've gone ahead and actually performed the inference, but instead of just saying, oh, okay, great, we have all these numbers now, it's nice to actually turn that into a physics result. To try and help me make this a little bit easier, I also assembled a small library that is in this exclusion directory here. Library is perhaps a bit of a generous term because it's more just kind of some scripts that were turned into an API, but I didn't want to have to deal with Python path issues. So if we drop in here and now just install this exclusion library locally, then we'll have that built very quickly. Okay, so now we have this exclusion library installed. So we can now go ahead, and I'm going to stop the intro to pyhf notebook, and I'm going to now open up this plot contour notebook. And so we're now going to attempt to visualize the exclusion contours from these CLS values. So we're first just going to import some widgets and some necessary things to actually do all this. And then we're now going to import this plot contour API from this exclusion library that we just installed, which again is just a small kind of toy library that I made for this workshop. You can't get this on PyPI at the moment. And we're now just going to load in the results that we generated. And now we're actually going to try and visualize these CLS values by interpolating between them and stitching them all into one exclusion contour. So there's some helper visualization functions here. This is all publicly available on all of the files that we're using are publicly available on HEP data. But given that these came from the Atlas experiment, we're going to be plotting using MPL HEP's Atlas style. So we're also going to be applying an Atlas-y style label to them. This is also just another helper function. As I said, we're going to turn on the MPL HEP Atlas style, and we're now going to this is just a helper function that extends the plot contour API that I mentioned, and also makes the things look a little bit nicer. And now we're going to actually plot these exclusion regions. And this will hopefully appear in a second. Well, okay, I'm not sure why this isn't showing up. This did show up on the other Coffee Casa, so I have to assume that there's something about the way that the visualization is interacting with the Jupyter widgets that were installed. So maybe what we can do instead is we can say access get figure save fig exclusion.png. Okay. Oh, okay. Well, now that worked. And so now we see that here we have the full exclusion contour for the plotted dots here. These are just the actual mass hypotheses points in which we actually have the CLS value evaluated. And you can see that we've interpolated between them with SciPy and stitched and basically stitched all together to get these exclusion contours. At the moment, I didn't make the exclusion library be able to deal nicely with having kinematic exclusions. So mentally, you should basically just take everything that's above this dashed line here and chop it off, so that you should basically only look everything that is below and to the right of this line. Okay, so this is nice. We've basically been able to go from from just published probability models to fitting them and actually getting a exclusion contour in just a few minutes. And if you had this kind of in a script, you could basically do the whole thing in probably just over a minute. So you can probably start to approach having limit setting be kind of almost a near interactive process. If we want to actually compare this though, so that you don't just have to take my word for it that this looks nice, we can actually also get the published exclusion contours from HEP data as well that are saved as t-graphs. So we're going to follow a procedure that Jordan Stark laid out in this reproducible Atlas SUSY summary plots GitHub gist. I'm not going to explain the specifics of it because we only have about 10 minutes left in this session and I'm already running behind. But essentially all we're doing is we're just actually going and again querying HEP data and getting the root files that actually contain the exclusion contours as t-graphs. And we're now going to use uproot to actually grab those out. And now we're going to plot those as well. And when we do that, then you can see that we have the published, observed, and expected exclusion contours, which look pretty similar, but we can do one better, and we can actually plot these both on the same figure to try and see how well they agree. And if we go ahead and plot that, then you can see that, so in the maroon, we have the observed limits that we got from our calculations, and then in the blue, you have the published ones. And while there are some visible deviations on the plot, they are not, directly overlaid. This is not an issue because if you actually look at the uncertainties that would be associated with this and also where the mass hypotheses are that were tested, all of this is within uncertainties. And I'm also just using default interpolation options for SciPy here. And so you could imagine that with enough tweaking of interpolation options, you can figure out some way to actually have these agree by eye. But the important thing is that they agree within uncertainties, which is nice to be able to see that they actually that we've been able to kind of reproduce a published result very quickly. And similarly, if we actually go and grab the plot from the paper, this will, here, I'm gonna have to zoom out again. But if we actually grab the published plot from the paper and compare it, my matplotlib skills were not good enough last night to be able to actually get these overlaid on top of each other, but you'll again see that the actual observed CLS values are well within, agree with the published ones well within the uncertainties. Okay, so in the final 10 minutes, I'm going to try and switch over and actually show some nice things with cabinetry using the same published probability models for this particular analysis. So if we now pop open this, let me, 1, 2, 3, this cabinetry workspace, or this cabinetry HEP data workspace notebook, then we're going to use these same probability models, but investigate how you can use cabinetry to be able to perform investigative inference really quickly and also get really nice visualizations while you're trying to design an experiment or design an analysis and also try and then perform the final inference as well. So we're going to import cabinetry to begin with, and then we're also going to go ahead and turn on logging at a level that gives us more feedback. We're doing this explicitly because we want to try and get more information as we're stepping through this notebook. If you're running, you probably, if you're running for a full analysis, you'd probably have this turned off to reduce the verbosity. So again, we already have these files, but we're going to just re-pull them down from HEP data. We're getting the published probability models once again, and then we're choosing to now investigate a particular mass hypothesis here. So here in the, going back real quick, if we look at all the mass hypotheses that were actually investigated, we're now going to be looking at basically this model point right here, which is at 800 and 300. So we're going to be now looking at that particular mass hypothesis with cabinetry. So we're going to download the probability models. We're going to load this particular mass hypothesis in as a workspace. So we're getting both the background and signal components there. We're now also going to serialize that as an actual probability model in the pyhf JSON format. And if we really quickly just investigate this with pyhf, then we see that we can get some, we can see that there's 8 channels, so 8 different signal or 8 different components to the analysis that are being fit simultaneously. And there's 10 different physics components with 120 parameters in total. Okay, so we're now going to just load. So we already have this workspace in memory, but if we were basically starting just from the serialized version, then we would just simply load in the workspace and then create from that workspace, extract out the model as well as the data. Okay, and now, so here you can see that cabinetry is also telling us, giving us more information on the specific modifiers that are being at play, all 120 of them, because we asked for improved verbosity. And now one of the really nice things about cabinetry is that it allows us to turn on, it allows us to, unfortunately, this doesn't look good when zoomed in like this a lot, but you'll have to believe me that if this is zoomed out and on a bigger screen, a really nice feature is that you can basically ask for a pre-fit yields table, and it will then construct for you for all of the different analysis regions what the actual predicted yields are going to be for all of the different model components. So yeah, I'm not going to try and resize this, but if you are following along by yourself at home, then I would encourage you to zoom out a little bit to try and see how nice that is. It's a really useful feature. But then you can also go ahead and using matplotlib, we can also visualize these model, we can actually visualize the model prefit as well. So we can actually, so here we've produced figures for all of the different analysis regions, and we can see that we have as this gets printed out, we can see that we have the prefit, visualization of the full model components as well as the data, as well as the ratio, and we have these for all of the different both signal region and control regions. But now if we actually want to perform inference, we can perform a maximal likelihood fit, and that's running now. This is running a little bit slower than before because we're also using IMINUE to be able to try and get the full uncertainties. And now that's finished, and we can see that we have also this summary from IMINUE that shows that we have valid convergence. And now we also have the model parameter uncertainties associated with all of those. And if we now perform post-fit visualizations, then we'll get all of those same analysis regions, but we're going to now get their post-fit model visualizations. And perhaps an easier way to see that is if we go into our figures directory and we look at both the, this is the post-fit, this is the pre-fit. So we now have these very nice visualizations where we have the pre-fit for this particular signal region, and we have the post-fit. And we were able to do both of these with just a single API call, which is really nice if you're trying to quickly explore an analysis, and also just be able to, here you'll notice that this these visualizations are just kind of popped out without any additional tweaking. But given that cabinetry takes the matplotlib API and extends it, that means you can still use matplotlib to be able to try and revise and improve these visualizations any way you want. You can also, of course, use MPL-HEP. And then what's also really nice is that you have the ability to visualize your polls for your model. And then additionally, you can also look at the correlation matrix and to try and reduce the information that is shown on the correlation matrix to maybe more useful, or interpretable scope. You can also apply a pruning threshold, which basically sets a lower bound for the level of correlation of one parameter with another for it to actually get shown here. So if we wanted to maybe just look at really the model parameters that are the most highly correlated, then we can just set a pruning threshold of 0.4 instead of 0.2, and we very quickly get this new visualization. Okay, so I think at this point I am well out of time. I did not get to a point where I could actually cover the cabinetry model configuration. I didn't think I was going to get to that. So I guess the question now is to Alex, if you want to, given that you're next and you're going to be kind of using the model configuration in your tutorial, do you want to take a few minutes there to cover that, or should I try and pull down the cabinetry tutorial and go through the rest of that?
In this case, since we're going to be waiting a bit in my talk, depending on how much we scale, we can cover that part in the next talk. I think that will work. But okay. Before we move over, I mean, we're certainly we have some time here to take questions that are related to what you've been showing.
Yeah, I realized that I was definitely much longer in the pyhf section than I thought I was going to be. So apologies there, but I'm more than happy to try and answer any questions that people might have.
No worries at all. Yeah, please, if you have questions, feel free to post them on Slido. You can also raise your hand here. We've had some interesting discussion happening in the chat related to FunkX and the problem of like having to sync versions of software being used in multiple places, perhaps a bit tangential to the talk.
Yeah. Yeah, since I can't see the chat because Zoom has decided to become a transparent window for whatever reason, Ben, I'm sure that you've probably also been responding there, but do you want to, given that you are our resident FunkX expert and also part of the FunkX development team, do you want to give a short response there?
I think I've covered most of it.
Okay.
In the chat, unless anyone has anything specific they want to bring up.
I have a question actually to Ben. So for example, for us to have a better integration of FunkX in coffee casa style workflows, do you envision something like possibility to running without Globus, but for example, with the tokens?
Fortunately, unfortunately, FunkX is being funded by Globus. So I would say quite unlikely.
I see.
Yeah, but everybody with a .edu email address does have a Globus account, whether they like it or not.
I see. Okay, then maybe we could chat if there is any chances how we can do this in a more like transparent way for the coffee casa. It could be nice to see what we can do. And also, other thing, do you have any like ideas about, let's say, what numbers did you ever test something like large enough as analysis grand challenge benchmark to see what is the speed up you could achieve with Feickert used as a backend?
I'm gonna let Matthew.
Yeah, so
more stress testing.
Yeah, so I think the short answer is we never really. For VCHEP 2021, we did tests across multiple published atlas analyses, and we kind of got to the point where we had enough resources on River that we were never able to really saturate it. So it was the fit times were not super variable because we had so many resources on River, and pretty much the thing that determined the amount of fit time was not the thing that determined the total fit time was not really how many points we were fitting, but how many but just basically the complexity of each individual analysis. We really never kind of hit like a limit. We haven't really kind of pushed to really explore, but for something like this, where, and I mean, here in this particular example, we've been using FuncX, but you can also imagine that you could be using Dask or something similar, where you basically like are using some service that just allows you to be fitting in a distributed manner, and taking advantage of the fact that since pyhf is a Python library, it makes it very easy to actually just define functions that you can serialize and distribute. And so you could imagine that, like, regardless of what service you're using, you could probably, as long as you have enough compute resources, you could probably fit for scale out your fitting to however many resources you have available. So we haven't really kind of hit a limit, but it would be great to try and find particular analyses that are really, really large, that have a huge number of mass hypotheses to consider, and try and use those. Something that's been brought up before is also considering things like minimal supersymmetric parameter scans, where you're just trying to look at many essentially like model variations, and then just see if you could be able to essentially like saturate an entire cluster. But we haven't really hit a limit yet.
I know we had like the usual problems with GPUs on our San Diego GPU cluster. Did you get much of a sense of throwing GPUs into the mix, what that does to us?
So we did have some issues with just being able to get the necessary like NVIDIA libraries working there, and we haven't revisited that since basically VCHEP. But when we did get them working, it did provide speed up, but it really wasn't as drastic as we were kind of as hoping for, because in the sense that if you have a huge amount of CPU resources and you can essentially just fit the entire analysis simultaneously, then if you can fit the entire analysis in essentially like 2 minutes versus 1 minute, then that's not necessarily that big of a difference. So while we were observing, on paper, like large speedups with the GPUs, that didn't necessarily translate into like human wall time that much benefit. So this is kind of an example of where for like, very kind of gnarly, like big models, being able to distribute across GPUs would be really nice. But for maybe like smaller models that aren't as complicated, then the advantage of being able to harness hardware acceleration is kind of diminished by the fact that as long as you have like a huge amount of resources to throw at it.
Got it. Okay, it will be interesting to because I feel like the next stage that we will be doing with our let's say shown software packages and services, we probably will try to do large stress tests and try to see how we can tune to achieve like real performance. So we should talk about like how we can do this in a sync way.
Yeah. Tomorrow I will also try and show some not necessarily PyHF related, but some Dask related examples that have been done in Atlas, and which I think will be a nice complement to what you're mentioning.